Let's work through an example of computing a line integral of a vector field in R3 over a curve in R3. So our curve C is the helix that we've seen before, given by R of t equals 2t, 3 cosine t, 3 sine t, where t runs from pi over 2 to 3 pi. This time our vector field f of x, y, z is given by z, y, and x. So again, what we're really doing here is for each point we have the tangent vector r prime, and we have a vector given by a vector field f, and what we're really computing is the scalar line integral of f dot the unit tangent vector ds. So we're really adding up all the tangent component of f to this curve as we we integrate that over every point in the curve. Using this parameterization, we can turn this line integral into a single variable integral with respect to the parameter t. So r prime of t is 2 minus 3 sine t, 3 cosine t. Now we don't need to take the magnitude of r prime. We can actually get away without ever computing that. Even though it's sort of implicit behind the scenes, we can avoid using it. Then the other thing we need is f of r of t, which is f of 2t, 3 cosine t, and 3 sine t. And so the first component of f is the third component of the input, so we get 3 sine t, and then the second component is just the second component, so we get 3 cosine t, and then 2t becomes the third component. Okay, so we have f of r of t, we have r prime of t. Now we're ready to compute the integral from pi over 2 to 3 pi of f of r of t dot r prime of t. So we're going to get 3 sine t times 2 is 6 sine t, and then plus, and 3 cosine t times minus 3 sine t. So I get minus a 9 sine t cosine t, and then I get plus 2t times 3 cosine t. So I get plus 6 t cosine t. And we're integrating all that with respect to t. Okay, so the antiderivative of 6 sine t is minus 6 cosine t. And then we can treat this, we can do a u substitution for sine t, or treat this as sine of 2t, which is what I usually do, and we get minus 9 fourths, cosine of 2t. So this is sine of 2t, so its antiderivative is negative cosine of 2t over 2, and this is really sine of 2t over 2, so that's why it's over 4. And then using u equals t and dv equals cosine t dt, we can do integration by parts. And I'm not going to go through the work, but this is going to be 6t times sine t, and then plus 6 cosine t. Alright, so this function is what we're going to evaluate from pi over 2 to 3 pi. So cosine of 3 pi is negative 1, so I get a positive 6, and cosine of pi over 2 is 0, so I get minus, really plus 0, doesn't matter. And then moving on, cosine of 2 times 3 pi is cosine of 6 pi, which is 1, so I get a minus 9 fourths here, and then I get plus, and then cosine of 2 times pi over 2 is cosine of pi, which is in the end -1. So I get, actually this turns out to be a minus 9/4. So then here I get sine of 3 pi is 0, and then minus sine of pi over 2 is 1, so I get 6 pi over 2. And then cosine of 3 pi again is -1, so I get minus 6, and then cosine of pi over 2 is 0, so that last term evaluates to 0. So simplifying here, the 6 and minus 6 cancel out. These become minus 9/2, and this is minus 6 pi over 2. So minus 9/2 minus 6 pi/2. So if I like minus 9 plus 6 pi all over 2. So this integral evaluated to be a negative number, and what does that mean? It just means that, so in this picture, f dot r prime, and so really f dot dr would be positive. On the other hand, if r prime is right here, say, and f is back this way, so my angle here is obtuse, then f dot dr is going to be a negative value. So it's just saying that f is, the tangential component of f is in the opposite direction of r prime, and more than it's not, or at least, so this weighted average, this integral, this number ends up negative because this situation is occurring more than this situation. And so it's perfectly reasonable to get a negative number here. Again, this f dot dr, all we need is f of r of t and r prime. We don't need the magnitude, so we compute both those in terms of the parameterization, r of t. It gives us a single variable integral, and we use single variable calculus to compute this and find the value of this line integral of f dot dr over our curve C.